Hi, I'm Teacher In. I work in the Water Conservancy department of our school. From now on, I will introduce some fundamental laws of fluid flow. Hello, everyone. Welcome to our class. Starting with this chapter, we're going to learn about fluid flow. We have already known that fluid is very different from solid. The striking thing in that is fluid, it is our object, contains a large number of particles, and these particles have relative movement in motion. So the traditional method that takes track of every object is no longer satisfying. We need a new way to describe our flow field. This is the reason for Eulerian method. Under this new method, we should build up some unique definitions or concepts for our flow. Based on that, then we come to three main equations, which are continuity equation, energy equation, and momentum equation. They are actually telling us the three main principles of our universe in fluid flow, respectively. What are these main principles? They are mass conservation, energy conservation, and momentum conservation, respectively. In fluid flow, they will have specific expressions that we have not seen before, but the physical meanings of them are not changed. Mass won't disappear, energy won't disappear, and momentum won't disappear. These three fundamental equations are the core of fluid mechanics, so they are our focus in learning. We will use them almost everywhere, very frequently, to solve flow problems. These are the three parts of this chapter. Lagrangian method is the one mainly used in theoretical mechanics. We put our eyes on an object that is in motion. The object locations X, Y, Z are our focus. The only variable is just the time t. Pay attention, coordinate A, B, and C are just markers, distinguishing that particle from other particles. They can be seen as initial coordinates of the particles. Therefore, they are considered as constants during the derivation process. Look at figure. For a particular fluid particle moving from A to B, coordinate functions x, y, and z show its instantaneous positions. Hence, velocity of the particle with the components ux, uy, and uz are partial differentials of position coordinates with respect to time t. The same with fluid acceleration. The locations x, y, z of that particle during the movement are still our focus. They just depend on time t, so we only do partial differentials with respect to time t. Identity markers A, B, C are still constant to time t. The difficulty of this method lies in that there are too many particles in our study field. It is impossible for us to learn all their movements. Actually, no need to do that. In general, we don't need to know specific movement of each particle. What we are concerned about are like this. Is there enough water in this place? Or Is the velocity here safe for us? Or how much is the pressure at this point, etc. We don't care who did it. Since Lagrangian method is not good enough for our usage in fluid, we turn to another effective method called Eulerian method. Here, we focus on spatial position no matter which particle goes through. So, for a flow field, we give up tracking particles and put our eyes on positions. Each position, which denoted by its coordinate x, y, z, has a specific velocity at the moment t. Here, you see we are given at first directly velocity distribution in time and space, not particle locations. We can even put the particles aside. We just care about the flow properties at locations. For example, in the figure, for moment t at location 1 with x1, y1, z1, any particle coming to this place will have a smaller speed. Samely, at location 2 with x2, y2, z2, any particle coming to this place will have a faster speed. If we have such velocity information everywhere in the flow field in all time, we can say we have known the flow very well. So this is a better way to describe the fluid flow. When we use Eulerian method to find the acceleration, we should pay attention to 2 points. First, acceleration is of an object, herein the fluid particle. So, in time interval dt, the particle generally has moved from one place to another. For example, in figure, position 1 to position 2. Second, when we take the derivative of velocity u with respect to time t, the position coordinates x, y, and z are functions of time t because x, y, z must be on the trajectory line of that particle. Hence, x, y, z are not arbitrary and not independent on time t. They are related by the particle moving route. So, this is a work for derivative of a composite function, where x, y, z are functions of t. Finally, under Eulerian method, acceleration is expressed by combination of 2 parts. One has just to do with time change in a fixed place, which is called temporal acceleration. The other has just to do with space at one moment, which is called convective acceleration. In other words, when fluid moves, the velocity change is caused by the time change and its location change in the flow field. In the following study, we may not calculate fluid accelerations. We introduced it here just for better understanding of fluid field description by Eulerian method. Here are some examples for understanding Eulerian method and its acceleration concepts. In figure here, there's a tube drawing water out of the tank. The height h is the driving factor of the flow. Large h will induce quick flow in the tube, or saying low h gives slow tube flow. Now h is constant. So, as an example, at location A, the current is steady, not change over time, both in case 1 and case 2. Therefore, the temporal accelerations in 2 cases are both 0. When determining temporal acceleration or local acceleration, we must stand on the same point to see the fluid current varying with time. Now we look at migrating acceleration or convective acceleration. In case 1, the tube has a constant diameter. The velocities, for example velocities on the center line of the tube, will not change. So migrating acceleration in case 1 is 0, 2. Thus the resultant acceleration is also 0. But in case 2, the tube is contracted. On the center line, the speed becomes larger and larger rightward. That is like a nozzle. Hence, the migrating acceleration in case 2 is larger than 0. Consequently, the resultant acceleration value is positive or larger than 0. Okay, in one word, while we work on local acceleration, we should fix on one point and study variation of its velocity over time. While on migrating acceleration, we should stop at a time moment to see the spatial change of velocity along the moving route. Now h is declining, which means the water surface in the tank is getting lower and lower. The force driving the flow are getting smaller and smaller. Therefore, the temporal acceleration at any point is less than 0, both in case 1 and case 2. As for migrating acceleration, in case 1, it is equal to 0. Thus the resultant acceleration, which is summation of the two kinds of acceleration, is less than 0. In case 2, the migrating acceleration is more than 0 due to the increasing speeds along the stream. So the temporal acceleration value is negative, while the migrating acceleration is positive. The sum of the two may be positive, may be negative. It depends on their values. According to the independent variables of velocity function, we classify flows in following. The first is to sort by time. If the flow is dependent on time, it's unsteady. Otherwise, it's steady. Velocity function of a steady flow includes only spatial coordinates, no time coordinates, and it has 0 temporal accelerations everywhere in flow field. The second is to sort by space. Dimensions of a flow depend on the numbers of spatial coordinates in velocity function. For example, velocities of one-dimension flow just depend on one spatial variable, such as x or flow distance. In this slide, I give some examples to you. Now all flows are steady flow. We just discuss the dimensions of the flow. In upper left, it's a flow in a straight uniform tube. The red arrows show velocity distributions on two cross sections. We can see velocity u changes with the radius r, little r, not change with x or angle theta. So it is a one-dimensional flow. In the upper right, it is a flow in a tube with variable diameters. The velocity u still change with the radius little r, also change with x, but not change with angle theta yet. So there are two spatial variables here. It is a two-dimensional flow. In the lower left, it's a wide, shallow, open flow, like water overflow from a dam. In the width direction, here normal to the page, there's no change with the flow, so the velocities, including magnitudes and directions, only vary with x and y. This is a two-dimensional flow. In the lower right, it is a complex flow that changes in all directions. It is a 3D flow. Well, trajectory or path line is a Lagrangian concept. In Euler method, we introduce concept of streamline. It is an instantaneous curve on which velocity vectors of each point are tangent to it. So, a series of streamlines in flow field can give us a clear view of flow motion at some moment. This figure shows us how to draw a streamline. The broken line 1, 2, 3, 4, 5, 6, 7, 8 will become a continuous curve when the distances between points are infinitesimally small. This curve is a streamline. Here are some examples of streamlines. The upper one is a flow around an airfoil or a wing. The lower is a flow around a cylinder. Here we give the view of the cross-section. Theoretically, we can draw countless streamlines in flow field. Because starting with any point, we can draw such a line, but no need to do that. Streamlines are just a tool to let us watch flow trend and find the velocity direction at a location. And we can see flow convergence or divergence. Here are basic characteristics of streamline. You can learn by yourself. I just explained number 3 and number 4. If two streamlines intersect, then at intersection there will be two directions for one velocity vector, right? Which is impossible, except the point speed is 0 with no directions. Okay, so there's a never velocity crossing streamline, which means no particles, no mass do that. Next concepts are stream tube and discharge cross-section. As in the picture on the left, take a closed line in flow field. Then all streamlines from all points of the closed line have made up a zone of tube shape. That is a stream tube. So stream tube is surrounded by streamlines, where fluid just comes in from upstream and comes out from downstream. No other entrance and exit. When the area closed by the line is infinitesimal, then the flow in the tube is called elemental flow or flow beam. We can imagine that in this case, the stream tube can be seen as a streamline geometrically. Discharge cross-section or flow cross-section is a surface which is normal to all streamlines in stream tube. It may be a flat plane or a curved surface, depending on the streamlines being straight and parallel or not, as you can see in the picture on the right. So, under such definition, there's no fluid moving along discharge cross-section. It only passes vertically through the discharge cross-section. Next is elemental flow and total flow. Elemental flow or stream tube flow is the flow in the infinitesimal stream tube. It is the smallest unit of fluid flow. All elemental flows within the boundaries made up total flow. In mathematics, total flow is integral of elemental flows. Look at the picture. This is a flow in a pipe. The elemental flow is drawn by dotted lines. The discharge cross-sections, sometimes we simply call it cross-section or CS. So discharge cross-sections of elemental flow are dA1 and dA2 respectively. The area of dA1 is so small that we can treat it as a geometric point with a point velocity u1 on it. So does dA2. The total flow is entire flow in the pipe, or we can say it's summation of the elemental flows. The total flow has an upstream discharge cross-section CS1 of area A1 and a downstream discharge cross-section CS2 of area A2. Flow rate is defined as a volume going through the cross-section in unit time. The SI unit of flow rate is meter cubic per second. So flow rate of elemental flow is dq, which is equal to UdA. It is the point velocity u times stream tube cross-section area dA. As for total flow, the flow rate Q is integral of elemental flow rate dQ within boundaries. According to the mean value theorem in calculus, the integral can be always written as a value V times cross-section area A. The value V is called sectional mean velocity. It is indeed the mean velocity of the cross-section. How to measure flow rate Q and find the mean velocity V? The simplest way to do that in lab is using a cup and a stopwatch. You guess it? Let the flow run into the cup and record the time. Measure the volume you get and divide it by the time cost. The result is Q. Then, with the flow cross-section area A, we can find the mean velocity V by the equation here. Okay, from these two equations here, we can infer that if flow rate is fixed, streamline convergence will lead to larger point velocities. Of course, divergence leads to smaller velocities. So, around a moving wing, the upper side air has quicker movement. The same with total flow. Small section will have large flow speed, while big section has smaller speed. That's why in summer we like to stand the narrow passage to feel cooler. Well, this page is about the two flow kinds. The definitions are given here. So, uniform flow is the simplest flow. The flow will not change along the stream. The shape and size of cross-sections, the velocities and their sectional distributions, and some other movement quantities are same on each cross-section along the flow paths. If it is a steady flow, then the fluid particles move with uniform speed in straight lines. so their accelerations are zero. Gradually varied flow is close to uniform flow. Hence, we usually use some properties of uniform flow to approximate it. For example, pressure characteristics. But rapid varied flow is far from uniform flow. It is often accompanied by discontinuity, inertial force, or complex phenomena. It is typically shown with dramatic change of streamlines, either strongly convergent, divergent, or bending. At last, what kind of flow do we focus on for our class? Well, in our learning, we just discuss the following fluid flow: continuous flow, homogeneous flow, incompressible flow, steady flow, total flow or one-dimensional flow, inside flow with solid boundaries, such as tube flow and channel flow.